Yeah, hello everyone. Welcome back to the afternoon sessions. I will be chairing the first session on database usability. Our first speaker this afternoon is Anna Fariha, who is an incoming professor at University of Utah. She will tell us about how data profiles can help explain data system malfunctions. Sorry.
Thank you, yeah, and everyone for inviting me for this talk. So today I'm going to talk about how certain data constraints can reveal causes of malfunction in data systems that learn from the data. In other words, how can we blame the data or certain data properties to explain some observed malfunction in systems. So before I get started with the particular work that I'm going to talk about, let's just talk a little bit about what are the common challenges that data systems that the users face. So a lot of different kinds of users now need to work with data. But even though data is now highly available, working with it effectively can be extremely challenging. There can be barriers of access where the users lack the means to effectively get the data they want, to retrieve the data. And then there could be barriers of understanding where the users struggle to interpret the results or just debug the causes of certain observed malfunctions or failures. And then finally, there is a barrier of trust where users do not feel equipped and confident to rely on the results that data systems are producing. So the ultimate goal of my research is to focus on aspects that remove this barrier. So as a more concrete example, think about a user who doesn't know SQL, but still wants to retrieve data from a relational database. So this is a usability barrier. And then think about a user who just trained an ML model over a data set. It was working fine, but now there is a new data set and the model is just failing or crashing or just having poor performance. So the user wonders what exactly happened, what's wrong? And finally, there is an issue of trust. And when an AI suggests us to do something, say, invest certain amount in certain stocks, so should I trust it? So one recent thing that happened is I was browsing Facebook and I got an advertisement that says ChatGPT said this is a skincare solution and it actually works. Sure, but I was very nervous. Like, would I actually put some products on my own skin because ChatGPT said so? I wouldn't do that. So this is a trust issue. This is the barrier that I'm talking about. So the ultimate goal of my research is to kind of meet the users of data systems where they are. It's to just bring the data systems more close to the user. So here I'm just showing a plot about different dimensions that the data systems researchers that they try to kind of these dimensions they try to optimize for. This is by no means exhaustive. There is performance. We always want our system to be performant, scalable, and so on. There is this correctness dimension. We want our systems to be accurate, reliable, and other stuff. But there is another dimension that I call is user-centeredness. So this dimension talks about other stuffs that are often overlooked or not prioritized while building data systems, such as debuggability, usability, then explainability, then trustworthiness, fairness, and so on and so forth. So HCI is an area that often tries to focus on some of these issues, but it mostly focuses on this understanding of user needs, interface design, visualization, and so on. But often there is little to no support from the system design level to support those things. On the other hand, the systems research focuses on the technology, architecture, algorithm to build effective and efficient system, but it's often unaware of this user-centeredness aspect. So as a result, I see there is a missing piece of puzzle that how can we connect these two things so that we can build systems while being aware that this kind of user needs need to be satisfied, and we can answer all this why not, how to question. So that is the high level research vision I have. And one of the piece of this work is what I'm going to talk about today is how we can explain the disconnect between data and systems. So often there is a lack of understanding in what impact the data has on system. So I'm not simply talking about data errors or system bugs. Rather, sometimes there are issues that a system is assuming certain things about the data and the assumption does not hold. So then there is a mismatch. So let's give you a very like toy example. So suppose a system is designed to handle data in US date format, but the data is in European or Australian date format. So the date formats are different. So what will happen is this unit mismatch or format mismatch will cause some system malfunction. So what I'm trying to do is debug this connection. Again, so I'm trying to identify such mismatches between data and systems. So this work is called data prism. So we are trying to kind of use a prism to see the data issues and stuff like that. That was the idea behind this name. And this is a joint work with my collaborators, Siam, Rowney, Juliana, Alexandra, and Devesh. And this work appears in Sigma 2022. All right, so let's take a closer look to a concrete example. So I'm here using a pretty famous US Census or adult data set. Suppose I'm trying to predict the attribute income from this data set. And the data set, say it looks like this. So I use it to train an ML model that can predict income. Now, an important thing is that often training ML models, an auxiliary goal in training ML models is to ensure fairness. So what it means is, from those who are not quite familiar, is the prediction error is equal in both kind of sensitive groups. So for male and female, we have equal rate of errors. For different kind of races, we have equal kind of errors. So the model is fair, its performance is fair across different sensitive groups. So after training it, we get just an 8% unfairness. So it's fine, it's possible, it's not that unfair. So I'm happy with this. So how did I do that? What I did is I wanted my model to be fair across gender. So I just dropped the sex column. So I think that the model doesn't even know the individual sex. So the model is supposed to be fair, and it worked fine. So I'm happy with my strategy. Now there is another data set. It looks kind of very similar to the first data set. There are kind of equal number of male, female, equal number of black and white people, equal number of married and unmarried people. So I use the same model or the same strategy. I'm not saying I'm using the same model, but the same strategy. Like, okay, let's drop this sensitive attribute and I hope the model will be fair. What happened this time is no, the model is very unfair. It's 95% unfair now. So what happened? Can anyone guess? Okay.
The condition on marital status, which was perfectly correlated with sex.
Yeah, you are correct. So what's happened is, in the first case, we had one married female, one unmarried female, one married male, one unmarried male. So there is no way to tell if a person is male or female by their marital status. So no correlation. Here, all females are unmarried and all males are married. So there is a perfect correlation between sex and marital status. So what's happening is, even though I think, oh, I removed the sex column, I'm fine, that marital status is acting as a proxy of a sensitive attribute, which wasn't the case for the first data set. So here, this certain data property is causing the model to fail. So these are the issues that we wanted to reveal in this work. So when I'm saying that issues, so what the issues could be? So one could be the classifier's accuracy decline. The other could be which I just talked about, the bias in prediction or unfairness. It could be crashing a program when, say, the system is assuming data is always 4 byte, but the data happened to be 4 megabyte or something like that. So again, all of these cases are the system is assuming something about the data which is not true. So what can we do? Here the idea is we want to blame the data, or specifically certain properties of data, what we call is data profiles. So that's from that idea, one thing to note is it's not about data errors or individual cell issues. It's about properties that are holistic over the data. So this correlation that I just showed, you cannot observe that by looking at individual rows. It has to hold holistically across the data set. So these holistic data properties or data profiles can give us hints about why for certain data systems don't work. So there are many other type of data profiles that we covered in this work that I'm not going into detail, but just some examples. For example, fraction of missing values. How many missing values are in the data? Fraction of outliers. What fraction of data are outliers? Or is there a particular functional dependency? So which is kind of like a correlation, but with more kind of database, more precisely defined thing. So given these are the unit of data profile, so now how does data prism work? So at a very high level, it has 4 steps. So I will just touch upon the ideas, I will not drill down. The first step is to find some discriminative profiles. What I mean is, so before even doing that, what we'll need is, we need a good data set and a bad data set. That good means for this data set, the system doesn't malfunction. For the bad data set, the system malfunctions. So we need a pair of them. Now what we do is, we try to see, say, these are the 2 data sets. What are the differences between 2 data sets in terms of data profiles? So what are the discriminating data profiles? So for example, in this picture, you can see there is this cloud, and in the other picture, there is no cloud. So that is a discriminating properties. So what we do is, from the data set, we find a pair of data sets, we find all such discriminating profiles. So you can see our actual issue is here in the second column. That was the discriminating one. That was the actual reason what happened, but there are other discriminating profiles. Now the second part is, among these discriminating profiles, there could be many such. Yes.
Where's the good and the bad that you showed us earlier?
Oh, so so the top one is a good data set, the bottom one is a bad data set.
Sure. Yeah. I mean, of course, that's very clear on this slide, of course. Yeah. But in the little table, can you explain the little table to us?
So these tables are just the table of profiles. This is not the data set. This is saying this profile is different in the good, in the bad data set. So the good data set, the age ranges are different. It's from, I think, 22 to 25. In the bad data set, the age range is larger. So in the good data set, there was no correlation between sex and marital status. In the bad data set, there is a correlation. So I'm just showing one example. I'm not showing the other one. So other one means that they were basically different. So it's just one case. So there is a counterpart of it, obviously. Yeah, thanks. So all right, so I have now found some discriminating profiles. Now I need to kind of rank them, which of these discriminating profiles are like the actual issues. So I think because of the interest of time, I'll not go into in further detail, but there are some heuristics we use to kind of rank them, like which of these profiles could be more promising candidates to be the actual causes. So one of the ranking criteria is just seeing which of these profiles connect to some attribute that other profiles also connect. So many profiles are connected to certain attributes, so those profiles are more promising. Again, these details are in the paper, but just high level idea is there are some heuristics we use, and there are also other heuristics like computing how bad is the profile, like how further is the profile from the good versus bad, versus, for example, if there are 30% outlier versus 32% outlier, this is a little deviation. But if there is 5% outlier versus 95% outlier, it's a huge deviation. So the more the violation is, the more probable is that that is a potential profile. So somehow we find these kind of candidates. Now, what remains is, we just know that this is a potential, it's a probable reason, but we're not sure. And from causality theory, we know that just correlation doesn't mean this is the cause. So what we need to do is, we need to actually intervene on the data or alter the data to remove those bad properties, and now check, okay, if I make this bad data set closer to the good data set, does it solve my issue? So what we do is, with each such candidate profiles, we kind of altered them. We say if there are too many outliers, we reduce number of outliers. So certain ways we do that. And if there's a correlation, we remove the correlation and see if the bad data set is slowly being moved closer to the good data set, at what point the malfunction stops. So when that happens, then we know, okay, now these are the actually causally verified causes of system malfunction. So that's the high level idea. And I'll just talk about very briefly about some results. So we had 7 case studies. Here I'm just showing example of 3 of them, like sentiment detection in some tweeted data. The second one I just discussed, there are correlation between attributes in the data, which was causing unfairness. And the third one was just some accuracy drop. And the high level result is that it's shown in number of how much intervention we needed to do. Intervention means how many times we needed to alter the data, test it, and then again alter the data, test it. So how many times we needed to do that? That is the intervention cost. And as you can see that Data Prism is our approach. It takes the fewest number of intervention compared to other state of the art. So the absent of a value means it couldn't even find out. It gave a wrong result. And as you can see, the other approaches take way more interventions to drill down because they sometimes enumerate a lot of spurious causes that are not even related. So that's the summary of the results. So yeah, that's kind of the end of the talk. In summary, that often the cause of system malfunction is certain properties of data, which is a holistic data profile. And we develop Data Prism that can find out those causes with a verification. It's causally verified that if you remove those causes, the malfunction will go away. And it takes a very few number of intervention than other state of the art. So thank you.
Great. Thank you, Anna.